we're going to talk about how to calculate volumes or solids of revolution, or volumes of the solids of revolution, I suppose, using the washer method. Big picture, what we will do is find the volume of the outside and subtract the volume of the inside. What this means in terms of a picture, before we were essentially talking about cylinders. So if this is my cylinder, that's what we would calculate. Now we're going to think of this cylinder as having an inside. And this cylinder looks like this. And what we want to find is the volume of this. So basically it's a cylinder with a hole in it. So if we think of uppercase R is the radius of the outside, meaning like here to the outside. And lowercase r is the radius of the inside. The radius of the inside would be here. Let's go the other side to here. Same on any side, obviously, definition of a radius. Then our volume of our solid would be pi r squared, which is the entire larger cylinder, minus that green inside cylinder, which is pi times lowercase r squared. And we can take out a pi, and this is pi times uppercase r squared minus lowercase r squared. If you think of the top view of this cylinder, you would see this circle and then an inside circle. And what we were finding would be this part. Lovely drawing on my part. Beautiful shading. All right. My children could do better. Moving on. Let's do some examples. So for the first one, if we have y equals 1/2 plus x squared is one of our functions, y equals x is our other function. We're going on the interval from 0 to 2. Revolved about the x-axis. So let's draw our picture. It's always how we start. Much of this will be just the same as the ones we've done so far for volumes. So if we sketch our figure here, 1/2 plus x squared looks something like that. Y equals x looks like that. So then our solid will look, we'll take this region and we'll reflect it. So it'll look like that. So now our solid, try to make it look three-dimensional-ish. There's our larger shape. And the part that we will subtract out is right there. It's a colorful picture. I don't know if I'd call it a good picture, but hopefully you can kind of tell what I'm getting at. Now if we draw a disc, draw our little lines here like it's a coin, and here's our radius. I'm going to take out a pi, and we know it's the integral uppercase R squared, or the outside function, minus R squared. And since when we drew these lines, they were horizontal, dx. So now if we look at our outside radius, we're going from here all the way out there. And that kind of coralish line was 1/2 plus x squared. So that radius is y equals 1/2 plus x squared. The other radius was only here to the blue line, which was x. So then this radius is y equals x. Now we want everything in terms of x because we have dx, so everything has to match. So we have pi times the integral. In terms of x, we go from 0 to 2. And then we have 1/2 plus x squared minus x squared dx. And again, technically, this will encompass the outside volume with the pi, and this will encompass the inside volume when we're subtracting those to get just the outside kind of washer, if you think of something with a hole in the middle. So now if we distribute this out a little bit, this will turn into 1/4 plus x squared, because we'll have 1/2 an x squared plus another 1/2 of an x squared, plus x to the 4th minus x squared dx. Conveniently, now some stuff will go away, and by some stuff I mean the x squareds. So the integral pi times the integral from 0 to 2, 1/4 plus x to the 4th dx. Not so bad in the end. Keeping the pi out, integral of 1/4 is 1/4 x. Integral of x to the 4th, x to the 5th over 5. We'll evaluate from 0 to 2. So we have pi times, well, 1/4 times 2 is 2/4, or 1/2. 2 to the 5th is 32 over 5. We plug 0 into both of those. Well, 1/4 times 0 is 0. 0 to the 5th over 5 is 0. So we get pi. I'm going to make this in tenths because that's a good common denominator. 5/10 plus 64/10. So pi times 69/10, which is 69 pi over 10. And this is the volume of our beautiful shape up here with the hole in it. For our second example, let's look at y equals the square root of x and y equals x squared revolved about the y-axis. So let's make our picture. It's about the y-axis, so I'm going to leave some space on either side. So if we draw y equals x squared, it'll look like that. Y equals the square root of x. It looks something like that. And since we're looking at y equals positive square root of x, that's really the only portion of the graph we need to deal with. Now if we reflect all of that, end up with, it's not great, huh? I'll try again. End up with this right there. Other part of square root of x over here. It's good enough. And then if we make it three-dimensional, something like that. We draw our disk. Looks something like that. And our radius. It's a little uneven, but we'll pretend it's not. So now we will set up our integral. So pi times the integral, r squared, which is the outside, minus r squared, which is the inside. We drew these lines on our disk. It was y, or rather they're vertical, so it's dy. So we have to have y's. So if we look at our outside radius, we start here all the way out here. That right there is y equals x squared. And if we look at the smaller radius, or the inside, only goes to there. Galaxy's not showing up great, but it goes to there, and that is square root of x. So that radius is y equals square root of x. So now if we write this, pi times the integral of x squared squared minus square root of x squared dy. This doesn't match. It's got to match the dy. So let's go back. Y equals x squared. Well, if I square root both sides, I get the square root of y equals x. So I can replace the x squared with the square root of y, because now it's in terms of y squared, minus, and let's look at y equals the square root of x. If I square both sides, y squared equals x. So now I can replace it with y squared squared. So now we have our dy at the end. In terms of how far it goes, you might be able to tell just by looking. If not, that's okay. Let's set square root of x equal to x squared. We square both sides. X equals x to the fourth. Divide by x. Starts to look kind of crazy, but essentially we know 1 is equal to x cubed. So then x has got to be 1. Still not entirely useful because we have a dy. But when x is 1, in either case, if you plug 1 into either function for x, square root of x or x squared, you will get 1. So 1, 1 is our point right there. Meaning, when we integrate in terms of y, we're going from 0 to 1. So when we do this, now we have pi times the integral from 0 to 1. Square root of y squared is just y, minus y squared squared is y to the fourth, dy, pi times y squared over 2 minus y to the fifth over 5 from 0 to 1. So we have pi times 1/2 minus 1/5. If we put 0 into either of those, we're going to get 0 minus 0. So pi, common denominator, 10, 5/10 minus 2/10, which is 3/10. So we'll end up with a volume of 3 pi over 10.